Hello there, you are welcome to the third unit of Module 1. In our previous class, we talked about vector and scalar quantity and how we can add them using graphical method and vector by component. Today, we shall be talking about how we are going to find the product of vector and scalar quantities. Let's start. This unit is the concluding part of vector and scalar concepts in elementary physics. In this unit, you will learn about unit vector and how to find the product of vectors and scalar product of vectors. In other words, we shall be doing multiplication of vector quantities. A unit vector is a vector that has a magnitude 1 and has no unit. Its only purpose is to point, that is to describe a direction in space. So when we have a unit vector which are given in notation I, j and k, where I points towards the x-axis, j towards the y-axis, and k towards the z-axis respectively. In the other time, we talked about components, how we resolve vector components. So we are familiar with this diagram because now last time we were able to resolve the vector components along x and y-axis. So this figure 1 is very familiar with you because here we find that this is equals to a cos theta, and we find that along the y-axis a sin theta. Now that we understand our unit vector, which can be I, j or k, we can describe our vector along ax, and we include our unit vector pointing towards the x direction and our ay along the y direction. And if we have the positive z-axis, we can as well have our k unit vector attached to our component along z. So we can have the direction of our unit vector like so. We have our I along x-axis, our y, our j along y-axis, and k along z-axis. If we are provided with a given vector of a and b, where a and b in this question represent a displacement, if we are to find the magnitude of 2a minus b, how do we do that? Okay, to do so let's move on to our whiteboard marker to implement this. Okay, so given these two displacement, a expressed like so and b like so. So let's solve this. So we have a, we can make our horizontal vector to be g, for example, to be equals to 2a minus b, and that gives us 2, and we write entirely our vector a, which is 5i minus 2j plus 3k. So we put our hat on our unit vector. Then we have minus here from the question. Then we have our vector b. So because of the minus sign, we need to put them in bracket. 6i minus 1j plus 4k. So if we open up this bracket, we have 10i minus 4j plus 6k. Then we open up this, we have 6i plus 1j minus 4k. So what we are left with now is to collect the like times. So here I mean I and I. So we can look at that. So we have, which is going to be 10 minus 6 I. Then for our k now, we have ijk. So we have minus, can put plus here, minus 4i, and this one, which is going to be plus minus 4j. So which is going to be minus 4 plus 1. Then we put our j out. So we collect the like times correctly. So now we have collected the like times for j. So let's do for k now. So for k, we have plus, we have our 6 minus 4. Then we have our k, and this gives us 10 minus 6. That gives us 4i. And we have this minus 4 plus 1 gives us minus 3j. And for the last component, we have 6 minus 4, which is positive k. So this is how to resolve a vector component like this. Okay? So now the next question is, how do we determine the magnitude of G? To determine the magnitude of G, we are going to use our parallelogram theorem, which is going to be, suppose we have this as gx squared plus gy squared plus gz squared. Here is my gx, this is my gy, and this is my gz. So finally I have my square root, which is going to be 4 squared plus minus 3 all squared plus 4 minus 2 all squared, and everything in my square root, and this is going to give me square root of 16 plus 9 plus 4, and this is going to give me square root of 16 plus 9 is going to be 25, and this is going to be 29. So, and what is the square root of 29? So here my final answer is 5.39.